Hello, I'm Christina, and this presentation is on aerodynamics. It covers much of the basics that you need to know when getting your private pilot's license. So we're going to start with the four forces of flight, which are lift, which is the upward force, weight, the downward force, thrust, the forward force, and drag, the rearward force. You can see this depicted on the screen. In straight and level unaccelerated flight, these forces are in equilibrium, with lift and weight being equal, as well as thrust and drag being equal. How do we get the plane to fly? Well, we add power, which increases thrust and lift, and away the airplane goes. Angle of attack is the angle between the chord line and the relative wind. The higher the angle of attack, the more the air flowing over the wing is disrupted. Upon reaching the critical angle of attack, the disruption is so great that lift suddenly decreases, which causes the nose of the aircraft to fall. This is otherwise known as a stall. What is drag, you ask? Great question. Drag is the force that resists movement of an aircraft through the air. There are two basic types, parasite drag and induced drag. The first is called parasite drag because it in no way functions to aid flight, while the second, induced drag, is the result of an airfoil developing lift. More about drag and the different causes can be found in the P-hack, which I highly suggest you read. The higher the angle of attack, the more drag is acting to slow the flight. The three axes of an aircraft: vertical, lateral, and longitudinal. The vertical is the left and right movement of the aircraft nose, or the yaw. This is controlled by rudder in the aircraft. The lateral axis is the up and down motion, or the pitch of the aircraft. This one's controlled with the elevator. And finally, we have the longitudinal axis, which is the side-to-side motion, or the roll, which is controlled by the ailerons. What are the forces of flight during turns? If you roll into a turn using only ailerons, your vertical lift decreases and your horizontal lift increases, and the airplane tends to descend. To keep your vertical lift the same, so you don't descend, you need to increase total lift. How do we do that? We increase the angle of attack by applying back pressure on your elevator. As you apply back pressure, you're actually raising the nose and getting a higher angle of attack during a turn. It's important to remember that it's not just level turns that increase your wing's angle of attack. In a descending base to final turn, you have a reasonable amount of back pressure to control your descent rate. Between your high angle of attack and low speed, it's just a recipe for a stall spin accident, which can be extremely dangerous and fatal. It's also important to note that when the aircraft banks, lift acts inward toward the center of the turn. In a normal turn, centrifugal force is equal to horizontal lift. In a slipping turn, centrifugal force is less than horizontal lift. In a skidding turn, centrifugal force is greater than horizontal lift. An easy cheat to remember this: K comes before L, and skidding is greater. When should you use rudder in a turn? I'm sure you're wondering. When entering a turn, rudder should be applied to move the nose in the direction of the turn. Once the aircraft nose is going in the right direction, rudder should no longer be necessary. Forward to stability. Stability is the tendency for the aircraft to return to its original state after being disrupted. There are two types of stability: static and dynamic. Static being the aircraft's initial response, and dynamic being the aircraft's response over time. Let's say we're flying at straight and level flight, and the aircraft encounters a gust of wind. If the aircraft returns to its original state before it encountered the gust, stability for that aircraft would be positively static. And as long as it stayed that way, positively dynamic as well. If you encountered the gust and the aircraft stayed in the new condition, it would be neutrally static. And if it continued on this path, it would also be neutrally dynamic as well. If, upon encountering the gust of wind, the aircraft continued in a manner opposite of the initial state, it would be negatively static. And if that aircraft continued on that path away from your original path, it would be negatively dynamic as well. The side effect of stability is that it allows for a degree of inattention even without the autopilot being engaged. Why is this important? Well, if you're flying and you release the controls for a short period of time, stability helps the aircraft stay on the path that you left it in. Okay, stabilize climb and descents. During a climb, angle of attack is increased, and anytime the angle of attack is increased, drag is increased as well, which means that the airspeed will decrease. In order to counteract this, we need to add power or thrust to keep the airspeed high. This is also one of the times that we need to be very aware of our airspeed and angle of attack because of the risk of stalling. Also, fun fact, when climbing, the aircraft climbs better in coordinated flight, and in order to accomplish this, right rudder should be applied. This is because of the left turning tendencies in the aircraft, which we will talk about more later. All right, descents. During descent, angle of attack is momentarily decreased, which means that lift is also decreased. So let's say we just lowered the nose and didn't adjust the power. What would happen to our airspeed? It would increase, right? Which could possibly lead to an unstable descent. To avoid this, power should be reduced to lower the airspeed. Why are stabilized approaches so important? Well, I'm glad you asked. The National Transportational Safety Board, or NTSB, is in charge of investigating aircraft accidents. And upon reviewing the numbers, they determined that a large number of accidents were caused because of unstable approaches. The number of times this occurred was so great that they issued an official safety alert. Everything on this slide was taken directly from that safety alert publication. What they found was that failing to establish or maintain a stabilized approach or continuing an unstabilized approach could lead to a landing too fast or too far down the runway, which would potentially result in a runway excursion, loss of control, or collision with terrain. They found that this happened regardless of the type of aircraft, the level of pilot experience, or whether the flight was being conducted under instrument flight rules or visual flight rules. A stabilized approach is the key to maintaining control of the aircraft and ensuring a safe landing. More can be read about this at the link on the bottom of the slide, and I highly recommend that you take a look at it. All right, I'm sure we've all heard of stalls. So how do we cause a stall? A stall is caused by exceeding the critical angle of attack. It's the result of lift decreasing because of the separation of airflow from the wing surface. While stalls are more common at slower speeds, they can occur at any airspeed. Super important to remember that. If left uncorrected or uncoordinated, a stall may result in a spin. There are a few different precursors to a stall. The plane will sometimes start to shake or buffer, and a warning light or horn will go off. This is super important. Why? Well, because we have another NTSB safety alert. This one is on preventing aerodynamic stalls at low altitudes. Let's take a second and think about why this would be a big issue. When are we at a low altitude? Well, when we're going to land, right? We also tend to slow our airspeed when landing as well. Hopefully, I know I do. This is the perfect time for a stall. Many stall accidents that occur in VMC conditions result when a pilot is momentarily distracted from the primary task of flying, such as maneuvering an airport traffic pattern, during an emergency, or when fixating on ground objects. So let me give you this scenario. You've just turned base and you failed to wind correct, or you didn't turn final soon enough. How do you correct to get to the aircraft lined up with the runway? Your first thought would of course be to add more bank and get turned around, right? So you're making a sharper turn than usual. Let's think about this for a moment. You're at a low airspeed and all of a sudden you're at a high angle of attack when you're turning. The chances of stalling are extremely high. This scenario was not only seen multiple times in the investigation, but with more experienced pilots as well as new pilots. So it's important to keep this in mind no matter what experience level you are at. Remember those left turning tendencies that I mentioned during climbs? Well, here they are. Torque reaction, P factor, corkscrew effect, and gyroscopic precession. I'm sure you're like, what do these mean? Well, let me tell you. Start with torque reaction. Most Western aircraft have engines that rotate clockwise when viewed from the cockpit. That's where torque comes into play. As you throttle up your engine for takeoff, the right turning direction of your engine and propeller forces the left side of your airplane down toward the runway. When the left side of the airplane is forced down onto the runway, the left tire has more friction with the ground than the right tire, making your aircraft want to turn left. P factor happens when the downward moving propeller blade takes a bigger bite of the air than the upward moving blade. This happens when your plane is flying at high angle of attack and when you're taking off in a tailwheel airplane. In both of these scenarios, your downward sweeping blade is at a much higher angle of attack than your upward sweeping blade. And with a higher angle of attack, the downward sweeping blade creates a much more thrust or lift, making your airplane want to yaw to the left. Corkscrew effect happens when your prop is moving fast and your plane is moving slow. What's a good example of this? Takeoff. During takeoff, air accelerated behind a prop follows a corkscrew pattern. As it wraps itself around the fuselage of your plane, it hits the left side of your aircraft's tail, creating a yawing motion and making the aircraft yaw to the left. Last tendency is gyroscopic precession, which is really confusing. Just know that when there's a spinning disc, the effect of that force is felt 90 degrees in the direction of the rotating disc. This applies for the most part to tailwheel airplanes when they lift their tail off the runway during takeoff. As the tail comes up, a force is applied to the top of the propeller, and since the propeller is spinning clockwise, that force is felt 90 degrees to the right, which creates a yawing motion to the left. Load factors. Load factor is the stress produced from any force that deflects the aircraft from straight flight. Load factors are important for two reasons. It is possible for a pilot to impose a dangerous overload on the aircraft structure, and because an increased load factor increases the stalling speed and makes stalls possible at seemingly safe flight speeds. It's also important to note that during steep turns, load factor is increased. Weight and balance. Aircraft are certified for weight and balance for two principal reasons. Number one, the effect of the weight on the aircraft's primary structure and its performance characteristics. And number two, the effect of the location of this weight on flight characteristics, particularly in stall and spin recovery and stability. Improper weight imbalance can cause structural damage and failures and has a negative impact on flight performance. Center of gravity, or CG, is the point over which the aircraft would balance. This is important because unequal load distribution causes accidents, and it actually affects the stability, controllability, and performance of the aircraft. A forward CG is a lot less dangerous than a rearward one. The latter becomes less controllable at low airspeeds and can be harder to recover from a spin and stalls in general. There's a lot more about the center of gravity in the PHAC, and I highly recommend that you go and read it. I just don't have time to go over it right now. Which brings me to my last NTSB safety alert, minding weight and balance. Improper or unperformed calculations can be fatal, and the NTSB found that between 2008 and 2016, the probable causes of 136 general aviation accidents were related to pilots improperly conducting pre-flight performance calculations for weight and balance, or not even conducting them at all. 1/3 of these accidents resulted in pilot or passenger deaths. So obviously, weight and balance is super, super important, not something to be taken lightly, and definitely something we should be doing every time, even if we think that we would be fine. We need to just double check and make sure. Once again, I highly encourage you to take a look at the safety alerts. They provide examples of accidents that occurred and what exactly went wrong, and are extremely helpful for pilots at any level of experience. Thank you, and that is the end of my presentation. Aerodynamics.